Hello, and welcome to our session on multiplexers. Multiplexers are a form of combinational logic that allow us to select one of many input lines to appear on a single output line. In this example on this slide, we have four possible inputs and only one output. And the goal of the multiplexer will be to select either A, B, C, or D and transfer its value to the output. And which input gets transferred to the output will be controlled by the select lines. Since we have four inputs, we need 2 to the 2. We have 2 to the 2 inputs here, 4. That means we'll just need 2 select lines to express or to control which of those 4 inputs gets transferred to the output. So for example, when little a and little b on our select lines are equal to 0, 0, then Q, or the output, will become equal to the value at A. When our select lines are equal to 0, 1, Q will take on the value of B, and so on. So how many select lines are required for a 27 input multiplexer? Well, 27 lies between the number 16 and 32. 16 is 2 to the 4th, and 32 is 2 to the 5th. 16, or 4 input lines, will not be sufficient to address 27 inputs. So we'll have to go with 5 select lines in order to be able to access all 27 of those inputs. So in this multiplexer, we'll have 5 address or select lines. We'll have 27 inputs. And by definition of the multiplexer, we'll only have one output. And the address lines, A, B, C, D, and E, will simply control which of the inputs is transferred to the output. We can design large multiplexers using much smaller building blocks. And in this example, we're going to look at being able to design a 16 by 1 multiplexer using 4 by 1 multiplexers. To do that, in our first stage of the multiplexers, we'll use the lower significant select lines to select each of a 4 block of inputs in the final multiplexer. So this first block, the select lines, will select one of the first 4 inputs in 0 and 1 and 2 and 3 to put on the output line. The next block, or next 4 by 1 multiplexer in this implementation, will also use S1 and S0 as the input or address lines to select the next set of 4 inputs in the multiplexer. And this is a 16 by 1 multiplexer, so there'll be 4 of these 4 by 1 multiplexers in the first stage. Once we select using the lower significant bits, S0 and S1, then we'll use another 4 by 1 multiplexer to decide which of the multiplexer outputs from the first stage will end up on the output line. And to do that, we'll use the 2 most significant bits in the select lines of the 16 by 1 multiplexer, denoted by S2 and S3. Those will choose one of the outputs of the 4 component first phase blocks in the 16 by 1 multiplexer, whether the first block, second, third, or fourth block, and put it onto that single output line that's characteristic of the multiplexer. And this gives us what is effectively a 16 by 1 multiplexer that can choose using 4 address lines, S3, S2, S1, and S0, one of 16 possible inputs between N0 and N15. Only one of those inputs will go to the output, and that will be controlled by these 4 select lines that enable 16 possible choices in which of the inputs will go to the output. A multiplexer can also be used to implement combinational logic, and we'll show a couple examples of how that's done here. In the first example, we're going to implement a combinational logic function f using an 8x1 multiplexer. There are 8 possible input combinations for the function f since there are 3 input variables. And we can simply implement this by noticing that we can actually just set x, y, and z equal to the inputs of the multiplexer itself. So if we just select 2 equal to x, select 1 equal to y, and select 0 equal to z, we're halfway to implementing this function using the 8x1 multiplexer. Now when x, y, and z are all 0, in the multiplexer we know in 0 is going to be transferred to out. And what we want is for the output to reflect the value of f, in this case 0. So we'll just set in 0 equal to 0. And we can continue doing that for this multiplexer to make sure that the accurate value of f in every case is transferred to the output. And in this case it's straightforward. We'll just attach all the inputs to the corresponding outputs f in the truth table. Well, this is an easy implementation of f here. It's not the only implementation. We can also look at implementing f using a 4x1 multiplexer and being a little bit more efficient about our implementation. So how will we do that? Well, there are a number of different ways, but in this example we can first note that there are only 2 terms in f. So why not just set the select lines for our 4x1 multiplexer to the terms in f? And since there are only 2 terms, we should be able to figure this out in a pretty straightforward manner. So here, if we set select 0 equal to yz0 and select 1 equal to x, y0, z, then we can take a look at what happens using the helper columns here in our truth table. So whenever these 2 functions, these 2 terms, are equal to 0, we notice that f is also equal to 0, which occurs in quite a few lines in the truth table here. So that means we can implement in the 4x1 multiplexer just by setting in 0 equal to 0. And that means when the 2 terms in f are equal to 0, f is also 0, and in 0 will get transferred to the output, which will then reflect the value of the function f. When x, y, z, x, y naught, z, and y, z naught are equal to 0, 1, which happens here and here, we notice the corresponding value of f is 1. And in that case, we can just set in 1 equal to 1 to make sure that when the 2 terms in f are equal to 0, 1 respectively, the output corresponds to a 1. In our last scenario, we have a 1, 0 combination here, which would correspond to the in2 value of the multiplexer. And when these 2 terms, or the address lines of the multiplexer, are equal to 1, 0, f is equal to a value of 1, so we'll just set in2 equal to 1 to make that happen accurately. And notice that nowhere does 1, 1 happen. 1, 1 does not occur when we implement the function f using the 4x1 multiplexer, so in3 in our multiplexer is simply a don't care. So in this session, we've taken a look at how multiplexers select one of many inputs and transfer the selected input to the output. They are often used to select from a variety of functions, for example, in an arithmetic logic unit to select among and, or, subtract, and, invert, and so on. but we've seen that they can also be useful for implementing combinational logic, so they're quite versatile in their uses. Well, that's all for multiplexers today. Thanks for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.